Okay, Module 2. Let's talk about DC fundamentals. In this module, we're going to talk about electric charge and electrostatic discharge. We're going to talk about defining conductors, insulators, and semiconductors. We're going to explain current flow in a conductor. Okay, and we're going to identify the basic components in a DC circuit. We're going to talk about Ohm's law. And we're going to talk about equivalent resistances, for example, when multiple resistors are in series or parallel. We're going to explain electric power and electrical energy from a DC fundamentals perspective. And then we're going to talk about Kirchhoff's voltage and current laws. And what's interesting here is these voltages and current laws are used in electric power systems, bulk power systems also. So it's very important to get to know some of these fundamentals, viewing it from just simple DC fundamentals. Okay? So let's talk about electric charges. There's positive charges and negative charges. Okay? And you've seen where you can take balls or metal objects and charge them up. If they're both positive, then they repel. If they're both negative, they repel. But when they're oppositely charged, they attract. So unlike charges attract. That's basic physics, okay? And we have the same thing with electric fields and magnetic fields. So let's talk about lines of force. You can see when we have like charges, the field lines repel each other, and yet when you have opposite charges, they attract. So you get a magnetic pull or a magnetic push. So we're going to talk about these types of electric charges. Okay? When it comes to static electricity is what builds up on power lines. It's, if you were to open up the circuit breaker on both ends of a very long transmission line, and those wires are just hanging out in the atmosphere, on insulators, just conductors, just pretty much electrically free floating in air, then a dry conditions or a light wind will cause a static charge to build up, and there can be voltages and thousands of volts of static charge building up on a line. That's a static electricity. Okay? You can take a balloon and you can rub it against your body or clothing and end up building up a static charge, and then it'll stick to a wall or something. Those are all static charges. Then you have lightning, which is an electrostatic discharge. You got the clouds creating a static charge up above, and then they short out with a lightning strike to ground. Those are static charges and discharges. Okay? Now, in an electric circuit, we're going to look at a little bit differently. We're going to talk about a voltage source, a battery, and we see the current coming out of the positive, going through the load, which is a resistor, and back into the negative. That should tell you right away that's conventional current flow. It's whole flow. When current is coming out of the positive, it's conventional or whole flow current. So that's what we're going to be setting our learning on DC about. Okay? So we have a voltage source, is also referred to as a power source. We have wire conductors where the current can flow, and a conductor by definition means it has electrons available in its valence bands to free flow between atoms. A good insulator would be material that the outermost electrons are tightly bound to the nucleus, and it would take a very high voltage or a high charge to push it away out of that atom, breaking it apart. That would be an insulator. Glass and porcelain and rocks, something would not have free-flowing electrons. They'd be good insulators. Okay? Now, a load here can be a resistor, like is represented by light bulbs or electric ranges or heating elements in a washing machine, or a load in general could be somebody's radio system, speaker system, TV sets, appliances. We're going to talk about the different type of loads later. There are basically three types. It's resistive, capacitive, and inductive. We'll be talking about those more later. But the load is the consumption device, the energy the activity that we're trying to create. Okay? So now let's talk a little bit about resistance fundamentals. When you have a wire, a skinny wire is going to have higher resistance than a large diameter wire. Kind of like with a water pipe. If you have a 6-inch PVC water pipe, you could put a lot more water through that pipe than you can a 1-inch PVC pipe. A 1-inch, if you try to put the same amount of water through a 1-inch that you're getting through in a 6-inch, you would really have to up the pressure, really have to increase the pressure in order to get the same amount of volume through a skinny pipe. Well, that's what happens in power systems. If you wanted to get the same amount of power through a skinny wire, you would have to increase the voltage. Okay? If you had bigger conductors, you could run less, you could have lower voltage to have the same amount of power flowing. But the main point here is I want to just make the connection that with wires, resistance is all about diameter. Okay? So a bigger diameter wire would allow more current to flow. Okay? And that's really what it is. And the bigger diameter wire has less resistance, and therefore you can have more current flowing. Okay, so that's just kind of the relationship we want to get there. So the type of material is the resistivity, whether it's copper, whether it's aluminum or steel, has different resistivity associated with the materials. Decreasing and increasing the cross-sectional area will change the resistance of the wire. Resistance also increases if you increase the length. Okay, and if you increase the temperature, the resistance will increase. Okay, and those are some fundamental things to keep in mind, because when you're dealing with large bulk power systems, long transmission lines are going to have higher resistance. Okay, the long transmission lines are going to be producing heat, and the heat in the wire is going to cause the wires to sag, and if they sag too much, they could touch a tree in the right-of-way and cause a short circuit and those types of things. So want to be able to make sure that you understand those relationships. Okay. The shape of the wire doesn't necessarily change the resistivity of the conductor. I'm going to take a pause for 1 second. Your head is actually right on the screen behind you, where I couldn't see the term. I was like, oh shoot, what is that saying? I'm reading the answer. Not a big deal. It's just that one particular one. What was that last thing I was trying to say? Thanks, Calvin. Okay, I'm going to start this one now. When we talk about wire sizes, we're talking about the American wire gauge when we're dealing with small sized wires. When you're dealing with electrical wires in your house or what have you, we're talking about a 10 gauge wire. It's going to have such a diameter or in millimeters, and for and the resistance for 1,000 feet or 1,000 kilometers. Okay, so you have charts like this. And one thing to notice is when the number gets bigger, you see on the left there it goes from a 10 to 12, 15. When the number gets bigger, the size is actually getting smaller. The diameter is getting smaller and smaller. And the resistance is getting bigger and bigger. So as the number gets larger, the wire gets smaller, the resistance gets greater, just like we were talking about. But in the American wire gauge, we're going up to 4/0, that's what that is. That's about the highest or largest size when we deal with in a wire gauge such as this. Then we go into what's called circular mills, and that's a much larger wire gauge standard that we'll talk about later that's used in power systems, where you're talking about some pretty large size wires. Okay, now notice that the resistance doubles about every 3 wire gauge numbers. Okay, so the resistance increases when the wire gets smaller. Okay, let's talk about a resistor. Resistor limits current flow. When you put resistance in a circuit, it limits how much current comes out of the source. So when we have resistance like this, and we measure, how strongly a resistor opposes the current flow, then that becomes our resistance value. Okay? The resistance is measured in ohms, and it's usually made of carbon wire or carbon in that little resistor. The different resistance values are available depending on the cross-sectional area and the length of the carbon wire. Now you notice those little color rings on the resistor. That tells you how much resistance is on that resistor. We're not going to get into color coding now, but you can look that up very easily, what the first color, second color, third color means, and what have you. Okay. We sometimes refer to grounding, or ground something that is grounded. Here we have the negative side of the battery or the voltage source grounded, okay? And that's common. In power systems, we might talk about a neutral being grounded. When we talk about grounding, we're really talking about connecting one side of the circuit to an earth reference, okay? We could have ground rods in the earth, and we're taking the negative side and grounding that circuit to the earth. Or maybe it's a chassis in electronic equipment. That battery is connected to the chassis, and perhaps the chassis is grounded. Anyway, that's what ground means. In this case, we have the battery negative side as the ground reference. Then there's the earth ground, where we can put the ground rods and the metal and ground grids and what have you into the earth and make an electrical connection with earth. Earth in general is conductive. It might not be as conductive as a piece of resistance or wire or copper wire, but it is conductive, especially alkaline soils, moisture, or you have fertilized or fertile soils, and you have real rich, moist soil. Those soils are very conductive. Okay? So if you use earth ground as a reference, a power line, for example, if it comes off the pole and lands on the ground, current will flow through the earth. And if we detect current flowing in the earth, we know we have a line down, we can trip the circuit breaker and clear the fault. These are some of the concepts that go in that you'll learn more about later. But earth grounding is a very common practice in DC and in AC. The symbol for earth ground in schematics, on circuit boards and those types of things look like that. It might be a little different on power system grounds, but that is a symbol for DC. We often see this symbol here used for earth ground. Okay? Now, we're going to talk about what happens when you put 4 resistors in series. What is the total resistance? And the answer is simple. You add them up, and the total resistance is the sum of the 4 resistances. And that's very basic for DC. So resistance equivalent is R1 plus R2 plus R3, etc. The more resistors you have in series, the more resistance you have total. Okay? When we replace a number of resistors connected in series with one resistor having the same equivalent resistance, there is no difference between the two configurations. Whether it's the equivalent resistance or all 4 components, it will limit the current the same. Okay, so one thing to note, and here this is actually bold, the equivalent resistor of resistors connected in series will always be larger than any of the resistance values individually. That's always a note. It's always larger. Whenever you add 2, it's going to be greater than either one. And that makes common sense. But when we talk about resistors in parallel, it has the opposite effect, and we'll understand that here in a few minutes. So here are resistors in parallel. We have 4 resistors in parallel. Okay? Now, this is a crazy formula. It looks harder than it is when you look at it. I remember I first studied that equation. I thought, whoa, boy, that's the first time I got into some complex math here. But what it means is, if you take the reciprocal of each resistor and add them up and take the reciprocal of that, you get the equivalent resistance. And that's good, but when you replace a number of resistors connected in series with one resistor having same equivalent, in the two configures is the same, but when you connect the resistors in parallel, you always end up with their total resistance less than the smallest resistance. So like we had in series, it's always going to be greater than any individual resistor. In parallel, it's always going to be, the equivalent is always going to be smaller than any one resistor. Now if you want to think of it this way, think of it in water pipes. If I had 4 water pipes in parallel, I could get more water through. It's going to have less resistance than having one. The more pipes I put to carry water flowing through and to get to the other point, the less resistance I have. So that's what happens here with electrical. Okay, so if we take 2 resistors and we put them in parallel, we're going to get an equivalent resistor. Okay? Now, when there's only 2 resistors, the simple formula says you multiply the two, it's the product divided by the sum. You multiply the 2 resistors together, divide by the sum of those resistances, and you'll get the equivalent. Now if you had 4 resistors in parallel, you can do that twice. You can take 2 resistors, their equivalent, product divided by sum. The other 2, product divided by sum. Now you have 2 equivalent resistors. Do it again to them. Product divided by sum, and you've just mastered that complex formula. Okay? So that's the theory behind resistors in parallel. Okay? So if the resistors happen to be the same value, if they're both 100 ohms, then the equivalent is 50 ohms. Okay? So that's just a simple one there. Now if they're all the same, you can use the formula that the equivalent is the number of resistors divided by the total number of resistors, if they're all the same value. Okay, so sometimes it's, I like to talk to telecommunications friends, and they'll, when they're trying to troubleshoot a circuit, if they don't have a 50 ohm resistor, but they have 2 100 ohm resistors, put 2 in parallel, put it in there, get the job done, go back and fix it permanently later. Using the resistor equivalency formulas, you can sometimes do what you need to do in a hurry. Okay, now let's talk about power in watts. Okay, now when we have the power equation, power is equal to current times voltage. Okay, that's a very fundamental formula. Power is voltage times current. First we talked voltage, then we talked current, then we talked power. It's the product of those two, and then we talked about energy. It's the product of those two times time. All right, so those 4 fundamental terms kind of come together here. Here we have a chart. It says power over, little diagram here. If you put your thumb over the P, it just says that power is current times voltage. If you put your thumb over the I, then current is power divided by voltage. Or if you put your thumb over the voltage, then it's power divided by current. Now I want you to note something here too, that it's very common to use the letter E or the letter V for voltage. In electric power systems and back in the Ohm's law day, it was all E. It's electromotive force, all E. But you'll see a lot of schematics, a lot of drawings use V as voltage. Just want to point that out. Now, if we substitute Ohm's law in for power, where Ohm's law is voltage is current times resistance, and put it into this power equation of power equaling current times voltage, we end up getting power is also equal to I squared R or E squared over R. Now, I want to point out a couple things. That first formula where power is I squared R, that is extremely valuable formula when it comes to measuring the losses in a power line. Now, think of a transmission line going 100 miles, and there's current flowing down it, and there's resistance of the wire, and it's on a hot summer day, and there's a lot of power flow, a lot of air conditioning load on. the current is going to be really high. Well, the current squared times the resistance of the wire is the power associated with heating that wire and heating up the atmosphere, stretching the wire and making it sag and touching a tree. Okay? It's the square of that current. And what you'll see is power companies do everything they can to reduce the current flowing in a wire for multiple reasons. One, if you can reduce the current in a wire a little bit, the heating is saved a lot because it's the square. If I can save a little bit of current, I've really saved a lot in heating. For example, if I can reduce the current in half, my losses go to a fourth of what they were. Or looking at it the other way, if the current in a power line doubles, I quadrupled the losses. I increased the heating tremendously. I've increased the stretching. It's all about current squared when we're talking about power flow in a wire. So I want to really point that out. You'll hear I squared R losses mentioned all your career in power systems because you're trying every day. People are trying to reduce that, whether they add capacitors, and we'll get into that, or whatever they do to the system, reactive resources, whatever they can do in the system to cut down on current in order to increase the power flow capability or decrease losses. We want to decrease losses as much as we can. Okay. Now when we get into energy, it's electrical energy is power times time. Okay, we talked about that earlier. So note to be not to be confused with E, EMF for voltage. This is a different E. That's why sometimes you use V for voltage. But anyway, we're talking about energy right now. And in electrical energy, you know, we're talking about watt hours or kilowatt hours. It's the watts times time. Okay? And when you pay your energy bill, you see how many kilowatt hours you use in a month? Maybe you use 600 kilowatt hours, and let's say you're charged, the power company charges you 10 cents per kilowatt hour, then your power bill is $600. So you use the kilowatt hours number, or it should be $60, excuse me, kilowatt hour number times your rate, and that's what your power bill is based on. Then they add all kinds of service charges and different things like that, or give you breaks if you conserve and things like that. But anyway, that's where the power bill comes in, your kilowatt hours on your meter multiplied times the rate. Okay. When we talk about power and energy, power is the rate of transferring or transforming work. In other words, a 1200 watt toaster, and energy is the amount of work performed over a period of time. We've talked about that pretty good. So let's just kind of get a little bit better feel for that. Here we have a 100 watt light bulb and we have a 50 watt light bulb. Okay? If we're going to talk about the energy, then we're going to say, okay, if we run the 100 watt light bulb for 1 hour, it would consume the same amount of energy as a 50 watt light bulb running 2 hours. Okay, so it's just a little bit on energy, just to understand energy a little bit better. Okay? When we talk about efficiency, now this formula always applies, what you get out versus what you put in. You know, I remember back in radio communications and transmitters and receivers, and a transmitter's output power divided by its input power was the efficiency of the radio or the transmitter. And you always had more input power than you got output power, and that's efficiency. It's that way everything. You know, if you look at a power plant, how much BTU energy do you put into the plant to get so many kilowatt hour energy out of the plant? You know, there's a conversion factor, BTUs to kilowatt hours. But the idea, you're always looking about how much you put in to how much you get out, and that's a percentage. So that's what we're talking about in power efficiency. Power out divided by power in. So a heater or a toaster represented by a resistor has 100% power efficiency because 100% of the power from the source is transformed into heat. But if you looked at the whole system, if you included the losses in the wires and all that kind of stuff, you'll see that you put more power out than what you, more power in than what you get out because of the heating of the wires. But an incandescent bulb has 2% power efficiency because 98% of the power from the source is transformed into heat and lost. Only 2% is transformed into light. What's interesting about light is we can only see a certain range of light. So even though the light bulb's putting out what looks like white light, there's infrared and ultraviolet that we can't see. It's all power is actually going into wavelengths of light that we can't even see. We can feel it. We know about ultraviolet and how it can, cause harm to skin, or infrared, how it produces heat, but not necessarily light. So that's where that comes in. So when there's a little bit of conversion efficiency is what they're talking about here, and the power efficiency must be as close to 100% as possible in a transmission system so that we don't have waste. So we're going to be trying to do that. And excessive heat or losses can occur when too much current flows or when the lost energy becomes too high. Now, a couple of the basic formulas or some of the concepts I think that's important to understand, that as you get going into power system operations, what have you, you need to know these certain fundamentals. And when it comes to series circuits, keep in mind that the current flowing in a series circuit is equal all the way through it. The current flow is equal, okay? The current is the same throughout the entire circuit. And the voltage divides across each of the resistors. If there are 3 resistors, and let's say it's a 9-volt battery, and the resistors are, let's say 100 ohms each, and there are 3 of them. Since they're the same, 3 volts will be dropped across all 3 resistors. The voltage drop of the resistors in series must add up to the source. So those are some basic concept in DC resistors. Now, the resistors are a passive element. That means they absorb energy. They don't produce it. And the source is an active element because it produces the energy. Okay, active components. Okay, here's where we are concerned about polarity. You see you have the positive and negative, and then you have the resistor voltage drops. Okay, they actually look opposite because of the way the current is flowing around, and it gives you a voltage polarity. Good to know, not necessarily critical in power systems, but good to know in DC fundamentals. Passive components, the current enters the positive polarity and leaves a negative polarity. There's just some detail there. When it comes to Kirchhoff's voltage law, this is what we just talked about. The voltage drop across all 3 resistors must add up to the source. That's Kirchhoff's voltage law. So the voltage source is the voltage on 1 and voltage on 2 plus voltage on 3 all the way up to the total number of resistors. Okay, or looking at it with the other convention, E. Okay, so E and V is basically the same. You might see V on schematics, you might see E on power system diagrams. Now here's the voltage divider rule. The voltage divides between the resistors proportionally to their resistance. By changing the ratio of the resistors, we can change the voltage drop to each one of them regardless of the value of the resistors. For example, when you look at that drawing, you see a 24-volt battery source and 2 resistors. They're the same resistance, so there's going to be 12 volts on each. Okay? Now, that says that the resistors are the same value. Now, if we take the same circuit and the current stays the same throughout the circuit, the voltage divides among the resistors in a way where The sum of the individual voltage drops across the resistors are going to equal the total source. That's Kirchhoff's law. But the greatest voltage is across the resistance with the greatest resistance. Okay, the equivalent resistance is a sum of the total resistors. It's larger than the resistance value of any one. So we got our total resistance. We can divide that into voltage and get our current. And then we can multiply Ohm's law, the different currents, or this current times the different resistances, and come up with the different voltage drops. And we also want to know that the power is in each resistor is dissipated by each resistor equals the total power supplied by the source. And the greatest power dissipation, is the resistor with the greatest resistance. Okay, these are just some fundamental facts about resistance. Now, in a parallel circuit, now we're going to be talking about current. If we have a voltage source and the voltage goes across both resistors here, we have a voltage source where the voltage is across both ends of both resistors here, okay? The current flowing down the resistors depends on the resistances of those two resistors. The resistance with the smaller resistance is going to have more current flowing through it. Remember, a bigger pipe has less resistance for water than a skinny pipe. If we have less resistance, we're going to get more current flow. So a high resistance is going to have less current flow than a resistor of lower resistance. If they're both the same, then I1 equals I2. Okay, so now, when there's more than one path for a resistance to flow, the components connected across the voltage source, that would be a parallel circuit. Current divides through the different paths, like we showed you here. The voltage is the same across the entire circuit. And when we talk about Kirchhoff's current law, and we talk about a node, a point, in a power system, this is like a substation. All the current coming in must equal all the current going out, or looking at it this way, all the current adds up to zero. Now, Kirchhoff's current law applies microscopically or in large situations. A very large power system transformer, power coming in must equal the power coming out, neglecting losses. But if you were to measure the power coming in and it did not equal the power coming out, then there's a problem with the transformer. We have protective relays that say, okay, if the power coming in does not equal the power coming out, it's a problem with the transformer, trip the circuit breakers, de-energize the equipment. That's basic Kirchhoff's law. Or if you look at an intersection, where all the cars coming into an intersection must equal the cars going out of the intersection, or the ones that are stuck in the middle aren't moving. Okay, so we have the same thing. So when we talk about a node, a substation, a point on a circuit or a diagram, all the current there must all add up to zero. Or all the current in equals all the current out, the net of which is zero. Okay. So we have a current divider rule here that says that the resistors are the same value, the current divides equally. A resistor with a higher resistance will have less current flowing through it than a current with lower resistance in a parallel circuit. Okay, so these resistors are the same in order to have a half an amp equal each other. Okay, more on parallel circuits in summary. The voltage stays the same across the entire circuit. The current divides among the parallel resistors. The sum of the currents flowing in each resistor equals the total current coming out of the voltage source, Kirchhoff's current law. The greatest current flow is in the resistor with the smallest resistance. The equivalent resistance is equal to a formula for parallel resistors and is always smaller than the individual resistance value. The sum of the power dissipated by each resistor equals the power supplied by the voltage source. And the greatest power dissipation is in the resistor with the smallest resistance. To summarize DC fundamentals, okay, we talked about static charge and electrostatic charge. Remember the lightning and the charged balls hanging from strings. We explained how current flows in a conductor. We defined Ohm's law. We determined the equivalent resistance of series and parallel resistors. We explained electric power and electrical energy. We discussed Kirchhoff's voltage and current laws. We've performed analysis of DC circuits having the same type configuration. And that basically sums up the DC fundamentals module for this particular section on electric power system fundamentals. Thank you.